Alright, in this video we'll be going through the 2014 electricity exam. The way I recommend you watch this video is to pause the video before every question, try the question yourself. Once you completed the question or get stuck, unpause the video to see how I go about getting the answer. The ideal transformer shown below has 3000 turns in its primary coil and 600 turns in its secondary coil. A 240 volt RMS AC power supply is connected across the primary coil. The secondary coil is connected to an external circuit. Calculate the RMS voltage across the external circuit. Alright, so we obviously know for our transformers, NP all over NS is equal to VP all over VS, where our P stands for primary and our S stands for secondary. It obviously says over here that we have 3000 turns in our primary and 600 turns in our secondary, and that's equal to the voltage of our primary, which is 240 volts, and we're trying to find the voltage of our secondary. And so therefore VS is equal to 240 divided by 3000 divided by 600, and this gives a VS of 48 volts. Calculate the peak voltage across the external circuit. Okay, so that 48 volts that we found is the RMS voltage of that external circuit, okay? And as we know, our VRMS is equal to our peak voltage all over root 2. Now, if you don't know where this equation comes from, I derive it in one of my videos in the electricity playlist, so you can go check that out. But in order to find the max voltage or the peak voltage, we just need to rearrange for V peak. And so we get 48 is equal to our V peak all over root 2. And so therefore 48 multiplied by square root 2 is equal to V peak. And so therefore we have a peak voltage of 67.88 volts. Explain why RMS values are often used to describe AC voltages. Alright, so as we know, RMS means root mean squared, okay? And so RMS at the end of the day is a type of average, okay? And if we take our normal arithmetic mean average, and the arithmetic mean is just what we usually use to find the average, so we take all the individual values and divide it by the amount of values that they are. If we do that for our normal sine function, okay, because there are equal amounts of points above 0 and equal amounts of points below 0, these cancel out. And so therefore our arithmetic mean ends up being 0. And so we need to come up with a new type of average which doesn't cancel out. Okay, and that voltage is the root mean squared. It's where we square the value, take the mean of those square values, and then square root the final answer. Okay, and so this ends up resulting in the fact that the RMS value has the exact same magnitude of a DC voltage that would deliver the exact same power output as the AC voltage that is being described. Okay, the external circuit consists of a resistor and an inductor as shown. The frequency of the power supply is 50 Hz. By drawing a phase diagram, show how the impedance of the external circuit can be calculated. Alright, so we know the phase diagram for our voltages is where we have the voltage of our resistor coming to the right like that, and the voltage of our inductor leads the voltage of the resistor by 90 degrees. Okay, so this is the voltage of our inductor. And therefore, applying vector addition to this, we have the voltage of our resistor, and this is the voltage of our inductor, like so. This resultant vector is the voltage of our supply, and so therefore our voltage of our supply comes up like so, okay? Now because this is a series circuit, even though our current is fluctuating, if we were to measure the current at any given time at any point in this circuit, the current would be the exact same. And so therefore, if we were to change this vector diagram, we would still have the voltage of our inductor coming up, but we can say that this is equal to I times the reactance of the inductor, and our resistance is I multiplied by the resistance of the resistance, and our voltage of our supply is equal to the current multiplied by the total impedance. And so because the current is the same at all points, we can just get rid of that in our phasor diagram, because the fact that the current is the same at all points does not change the shape of our vector diagram, okay? It will change the values itself, but the shape of the vector diagram does not change, okay? And so from here, we can draw another vector diagram off of this and say that the resistance vector comes right here, our reactance of our inductor comes up over here, and the total impedance comes up like so. We are given the resistance of our resistor, so this is 3.69 ohms, okay? The reactance of our inductor is not given, however, we are given the frequency and we're also given the inductance. And we know that the reactance of our inductor is equal to omega L, and our omega is equal to 2 pi F. And so the reactance of our inductor is equal to 2 pi times 50 times 16.5 times 10 to the negative 3 henries, alright, because this is millihenries, alright? And so this gives a value of 5.18 ohms, okay? And so this is 5.18, and so therefore Z is equal to square root 3.69 squared plus 5.18 squared, and this gives a total impedance of 6.36 ohms. A capacitor is added to the external circuit, causing the circuit to be at resonance. Determine the RMS voltage across the capacitor. Alright, so when the circuit is at resonance, that is when the reactance of the inductor is equal to the reactance of the capacitor. Now we just found out the reactance of our inductor, and that was equal to 5.18 ohms, and so therefore the reactance of our capacitor is also equal to 5.18 ohms. As V is equal to IR, and therefore I is equal to V all over R, we are able to find the RMS current, okay? Obviously, this will also be the RMS voltage, okay? We found the RMS voltage in a previous question, and that was 48 volts, divided by our resistance, and in this case, our resistance is 3.69, okay? The reason why we're using resistance in this case and not total impedance is because when the reactance of the inductor and the reactance of the capacitor are equal, this means that the total reactance of the circuit is equal to 0. And so therefore, as our total impedance is equal to square root XL minus XC squared plus R squared, if our XL and XC are equal to each other, then this value just goes to 0, and so Z is equal to square root R squared, and so Z is straight equal to R. And so the only impedance value in the circuit is our resistance. And so this gives a RMS current of 13.01 amps, and so therefore the voltage across the capacitor is equal to the current multiplied by the reactance. We just found our reactance, and we just found our current, and so therefore 13.01 times 5.18, and this equals to 67.38 volts. The circuit diagram shows two batteries connected in a circuit. The internal resistance R1 of the 11 volt battery is 2.7 ohms, and the internal resistance R2 of the 10 volt battery is 2.5 ohms. Switches S1 and S2 are closed, and switches S3 is left open. Show that the current in the circuit is 0.331 amps. So in this case, switch 1 is closed and switch 2 is closed, okay? But switch 3 is left open. Alright, so there are two ways in which we can solve this problem. The first one being we can use Kirchhoff's voltage law. If we start over here, we see we have an 11 volt rise, okay? So we can start off with an 11 volt rise. And we come down here, okay, because we're not going to come here because the switch is open, okay? So that means there's a break in the circuit, so no current will flow through there. As we can see, we have a 10 volt that is opposing the direction in which we are moving in, okay? And so therefore we can minus 10 volts. And then as you can see here, we're going to have a voltage drop across this 2.5 ohm resistor, okay? That's the internal resistance. And so we minus 2.5 I, alright? And once more, we're going to get a voltage drop across this 20 ohm resistor, and so we minus 20 I, and then we come up here, we're going to get another voltage drop across this 5 ohm, so minus 5 I, and another voltage drop across this 2.7 ohm, and so we minus 2.7. And that's all equal to 0. And so 11 minus 10 is 1, minus all these is equal to negative 30.2 I, and that's equal to 0. And so therefore 1 is equal to 30.2 I, so 1 all over 30.2 is equal to our current, and this gives a current value of 0.0331 amps. And as you can see, that's the value that we're trying to find. Another way in which we can solve this is we can see that we have an 11 volt and a 10 volt opposing each other, okay? And so therefore the total EMF is going to be 1 volt in the circuit, okay? We see that over here, okay? And then we can simply calculate the total resistance in the circuit, and that's going to be equal to 30.2. And we can say that V is equal to IR, and therefore I is equal to V all over R. And so therefore 1 divided by 30.2 is equal to 0.0331 amps. In which direction will current be flowing through S1? Explain your answer. So the current will be flowing in this direction right here, okay? So in the anti-clockwise direction, so going in this direction right here, okay? The reason for that is because the positive terminal of this 11 volt has a higher potential than the positive terminal of this 10 volt, okay? And so therefore current flows from higher potential to lower potential, and so therefore the current will flow in this direction. Another reasoning in which you can explain this is by saying that when Kirchhoff is carried out, when we carry out Kirchhoff's voltage law, we get a positive current value, meaning that when we assume that current is flowing in this direction, we get a positive answer, meaning our assumption was correct, okay? And so you can explain it in that way as well. Switch S3 is now closed so that all three switches are closed. Show using Kirchhoff's law that the current through S3 is 1.87 amps. Alright, so we have our diagram right here. All three switches are closed, okay? And we can define three currents, this being I1, this being I2, and this being I3, okay? And we know that I1 plus I2 plus I3 are equal to 0 because the algebraic sum of all currents leaving a node is equal to 0, okay? And so using Kirchhoff's voltage law in terms of I1, we get 11 minus 2.7 I1 minus 5 I1, and that's all equal to 0. And then doing the same for I2, we get 10 minus 2.5 I2 minus 20 I2, and that's all equal to 0. And so therefore, from here, we can say that 11 minus 7.7 I1 is equal to 0, and so therefore 11 is equal to 7.7 I1, and so therefore I1 is equal to 11 all over 7.7, and that's equal to 10 divided by 7 amps, okay? Keeping it in fraction form in order to keep whole values. And so therefore we can do the same for this, and we get 10 minus 22.5 I2, and that's all equal to 10 is equal to 22.5 I2, and so therefore I2 is equal to 10 divided by 22.5, okay, amps, keeping it in fraction form in order to keep whole values. And so therefore, we know that I1 plus I2 plus I3 is equal to 0, okay, and so therefore I1, which is equal to 10 over 7, and I2, which is equal to 10 all over 22.5, okay, and I3 is what we're trying to find, so therefore 10 over 7 plus 10 divided by 22.5 plus I3 is equal to 0, and so therefore I3 is equal to negative 1.87 amps. There we go. And as you can see, that is the value that we're trying to find. Now, just remember that the negative in this case just means that instead of the current going in this direction right here, it is in fact going in this direction right here. Okay, switch 1 is now open, leaving switch 2 and switch 3 closed. After this, the circuit has been operating for some time, the 10-volt battery starts to go flat. Our students suspect that this is caused by an increase in the internal resistance. Explain what effect a changing internal resistance has on the power delivered to the 20 ohm resistor. A full answer would include some sample calculations. Alright, so if we were to calculate the power before there is an increase in the internal resistance, as we know the power used by the resistor is given as P is equal to I squared R. Okay, we have our resistance because that is just the resistance of the resistor. However, the current is equal to the EMF divided by the total resistance, where the total resistance is equal to the resistance of the resistor plus our internal resistance, which is 2.5 ohms. Therefore, plugging in our numbers, we get 10 all over 22.5, and this gives a value of 4 over 9 amps. And I'm going to leave it like this in order to keep whole values. Okay, so therefore the power used by our resistor is equal to 4 over 9 squared multiplied by the resistance of 20 ohms, and this gives a power of 3.95 watts. There we go. Okay, so now that we have some sample calculations, these are our base calculations, we can now see what will happen if we increase our internal resistance. So if we increase our internal resistance, therefore our total resistance is also going to increase. And so therefore, as our total resistance increases, therefore our current throughout this circuit is going to decrease. And once our current decreases, therefore the power delivered to the 20 ohm resistor is going to decrease, okay? Another way we can look at this is we can say that the voltage across our 20 ohm resistor is equal to the terminal voltage, okay? So these two voltage values are equal. The reason for this is because our two ends of our power supply share a node with the two ends of our resistor, okay? And so their voltages are going to be equal to each other. And so therefore, if our internal resistance increases, therefore as our terminal voltage is equal to our EMF minus our lost volts. If our terminal voltage increases, that means that there's going to be a greater voltage drop due to our internal resistance. And so therefore our lost volts is going to increase, meaning our terminal voltage is going to decrease. And so therefore we can also say that P is equal to V squared all over R. And so therefore if our terminal voltage decreases, therefore the voltage across our 20 ohm resistor is also going to decrease, and so therefore we can also say that the power delivered to the 20 ohm resistor is going to decrease. So you can do it both ways. I would recommend this way, 1, because it's easier to use sample calculations, which is what they require, and 2, this is the method that the marking schedule uses as well. But this method should also get you full marks because technically it is valid. In the circuit above, switch B is kept open and switch A is closed, allowing charge to flow onto the plates of the capacitor. Explain why the voltage of the capacitor rises to the voltage of the battery. Alright, so switch A is closed and this one is kept open. Okay, so initially, there is no charge accumulated on the capacitor plates. And so therefore, when the switch is closed, charge will flow from the battery onto the capacitor plates, okay? As charge begins to accumulate on the capacitor plates, the charge that has already accumulated on the capacitor plates will repel any oncoming charge, okay? And so therefore this slows down the flow of current, and so therefore the current begins to drop off in the circuit. This will continue to happen until the capacitor is fully charged. At this point, once the capacitor is fully charged, the current will almost be at zero, and this happens because the potential difference across the capacitor is equal to the potential difference across the power supply. And this makes sense because we have two opposing EMFs, which are equal in magnitude, and so therefore no current will flow. Okay, and so that is why the voltage of the capacitor rises to the voltage of the battery. When the capacitor in the circuit is fully charged, it carries a charge of 8.6 times 10 to the negative 3 coulomb. Calculate the energy stored in the capacitor when it's fully charged. We know that the potential energy in a capacitor is equal to half QV. As stated in the previous question, when the capacitor is fully charged, it's going to have the exact same voltage across it as the power supply. So that means our voltage is 12 volts, okay? And we are already given our charge. And so we get half 8.6 times 10 to the negative 3 multiplied by 12, and this gives a value of 0.0516 joules. There we go. The graph below shows the relationship between the voltage and time as the capacitor charges. Sketch another curve on the graph to show the effect of an increased resistance on the charging of the capacitor. Alright. As we know, our time constant is equal to RC, where our R is our resistance and our C is our capacitance. If our resistance has increased, therefore our time constant must also increase. And this means it takes a longer time for the voltage across the inductor to rise to 63% of its previous value. Okay? And so therefore, if it takes a longer time to go to 63%, let's say 63% is like roughly right here. If it takes a longer time, that means the graph is going to be slightly less steep. It's going to eventually flatten out to the same value. Okay, so previously it took this amount of time to go to 63%, but now it's taken this amount of time, okay? So a slight increase in time. And this should be perfectly straight, but you know, whatever. Now switch A is opened and switch B is closed. The current changes with time. Explain the effect that inductors have on the currents that change with time. Alright, so now looking at this diagram, switch A is open, but switch B is closed. Okay, there we go. Alright, so if the current is changing, therefore the flux within the inductor is also changing, and as we know, the EMF reduced by the inductor is equal to negative L, change in current, all over change in time. Okay, therefore, as there is a change in current, therefore the inductor is going to induce an EMF. And this induced EMF is going to act in a direction to oppose the change that causes it, okay? And as you can see, we have disconnected the power supply from the circuit, and so therefore the only charge that is stored within the circuit now is the charge on the capacitor plates, okay? The capacitor is going to discharge itself, therefore the current is going to start to flow, and flow from a max value all the way to a minimum value, because the capacitor only has a limited amount of charge. However, due to this inductor is going to oppose that change in current, right? It's going to oppose the change from max to minimum, okay? And so therefore, it's going to take longer for the current to drop to a minimum value, because the inductor actually wants the current to continue to flow. Again, the inductor wants to oppose the change, okay? And so if the change is from max to minimum, it wants to keep the current at a max value for as long as possible. So it's going to try to keep the current at a max value, therefore increasing the amount of time it takes for the current to drop to zero. And so you can write that in. Discuss how the energy is stored in the capacitor and the inductor at the instant switch B is closed, and then while the capacitor is discharging. Alright, so energy stored in the inductor is given by this equation right here, and energy stored in the capacitor is given by this equation right here. Okay? When the capacitor is fully charged, the energy is stored within the electric field of that capacitor, okay, between the two plates. And as we know, when the capacitor is fully charged, that means the voltage is at a max value, and so therefore we have the maximum amount of energy stored in that capacitor, okay? Also, when the capacitor is fully charged, there is no current flowing, and so therefore, as you can see from this equation, if our I value is 0, therefore the energy stored in our inductor is 0. So now, as the capacitor begins to discharge itself, the voltage across the capacitor is going to decrease, also the charge on the capacitor is also going to decrease, and so therefore the energy stored in the capacitor is going to decrease. But as the capacitor discharges itself, a current is obviously going to flow because now there is a movement of charge. And so now because there is a movement of charge, current flows. And so therefore, because the energy stored in the capacitor is equal to half Li squared, because there's a current present, there is going to be energy beginning to store in the capacitor. And so as you can see from this relationship, the energy stored in the inductor comes from the energy stored in the capacitor. Okay, and also just like the capacitor, the energy within the inductor is stored within the magnetic field. Okay, and so that will be it for this video. See ya.